Hey guys, welcome back to chapter 16. This video we're going to work through another weak base problem. So the base hydralazine N2H4 has a Kb value of 1.7 times 10 to the negative 6th. What is the pH of a 2 molar solution? So go ahead and pause the video, get as far into this as you can, and I'll catch up with you. All right, so the first thing we're going to need to do is we're going to need to draw the equation for the ionization of hydralazine. So this base, again, isn't one of those bases that jumps off the page at you. So I did help you with a couple different words like the base, hydralazine, and then the fact that it's a Kb value. So that's how you know that it's a base. So this base is going to be put into a water solution, aqueous solution. And the base, so remember, bases are proton acceptors. So we've got 2 nitrogens, 4 hydrogens. It's going to take on another hydrogen. It doesn't really matter how you write this, because it really doesn't have a lot to do with the problem. So you could write it like this, or you could add the hydrogen in with the other ones. It really doesn't make a big difference. However you want to write it out, that's up to you. Or you could use the generic one that we used in the last problem. All right, so if this is our base, this is our proton acceptor. That means water is acting as a proton donor. So if it gives away one of its hydrogens, it's going to be left as just hydroxide. Once we have that, we've got our ice table and our Kb value to take care of. So Kb is going to be products over reactants. So that guy is going to have a plus charge. And hydroxide. And again, water is not included. And that's going to be our equation. Then we'll have our ice table to fill out. All right. So what is the pH? It tells us the molarity of the solution prior to equilibrium. So molarity of the solution is going to be 2 molar, no mention of the other two. So again, we're always going to assume that they're 0. The molarity of the ones that were 0 can only go up. And then that means the molarity of the original can only go down. So we've got 2 minus X, X, and X. Okay. Now we are ready to plug through this problem. So our Kb value is, just click back real quick. Kb value is going to be 1.7 times 10 to the negative 6. Our concentration of our products at equilibrium are X and X. Concentration of our reactant is 2 minus X. Again, use quadratic if that's your cup of tea. I'm going to go ahead and use X is small, so I'm going to get rid of that variable. And it's going to clean up to 1.7 times 10 to the negative 6th equals X squared over 2. Now I'm going to work on getting X by itself. So multiply by 2. Those cancel. And so I'm going to get X squared equals, plug this into my calculator, 1.7 times 10 to the negative 6th times 2 equals 3.4 times 10 to the negative 6th. And then to get X by itself, we'll take the square root. So X equals 0.0018. Let me just take a moment real quick to validate it. So we're going to take the 0.0018, divide it by 2, multiply by 100. So 0.0018 divided by 2 times 100 is 0.09%. So certainly this x is small is incredibly valid. It's well under that 5%. Okay. All right. So clicking back to our ICE table, remember we are interested in this hydroxide concentration, as that's what's going to lead us ultimately to pH. So I'm going to rewrite this as my hydroxide concentration is 0.0018. And again, you can take either path to getting to pH. I'm going to pick a path this time just to save a little bit of time. So I'm going to go to POH first. So POH equals the negative log of 0.0018. So POH equals negative log 0.0018. POH is 2.74. And then pH is just 14 minus POH. So pH equals 11.3. Okay, and that's our answer. Does this make sense? Well, of course, yes, it makes sense. I told you that hydralazine was a base, and so a pH of 11.3 is a basic pH. Hope you guys found this helpful.